Hi everyone, my name is Omar. I'm a software engineer at Cesium. I'm excited to share with you today some of the integrations we've been working on with Bentley to make it possible to use Cesium data across the iTwin platform. Now before we jump in, I want to give you a little background about Cesium and explain what 3D Tiles is, which is an open standard we pioneered that makes it possible to connect data from different providers all into the same scene in iModel or in any compatible client. And then we'll look at how the integration between the Cesium platform and iModel works. So what is Cesium? In short, it's the platform for making 3D geospatial data valuable to users. Now there's a few parts to this platform. Many of you may already be aware of Cesium.js, our open source JavaScript engine that people have used to build apps in everything from aerospace to urban planning to construction and agriculture. And up here we've got Cesium Ion. This is the commercial platform where you can access curated 3D data. For example, this is where a lot of applications get global satellite imagery and 3D terrain, like context capture, for example. This is the default terrain layer if you use the viewer there. The key part here is that you can bring your own data to fuse it on top of these global layers. For example, you can have drone flights on an area where you have a project. You'd upload that to Cesium Ion, convert it to an efficient format that can be streamed over the web, and then because this is all using open standards, you'd visualize that in clients like Cesium.js or iModel. Now here's an example so you can see how all these pieces fit in together in the real world. This is a company called TrendSpec that has a digital asset management platform that's built on Cesium. The idea here is you can log in, see the latest drone survey that was collected, maybe make some measurements and request a second opinion, and then submit a report. You can also see how a site has changed over time or do a side-by-side comparison of two different captures. And one thing to highlight here is that even though this is all running in the browser, you're not looking at an approximation or a simplification of the mesh. This is because the data is tiled with 3D tiles. So you don't have to worry about whether an artifact you're looking at is like an actual scratch in the structure or just an artifact of the simplification. Which is kind of critical when you're looking at this kind of infrastructure. So here, the users of the app upload their own data that they collect, which is tiled and hosted on Cesium Ion, and visualized on top of the global base layers from Cesium Ion. So what exactly is 3D Tiles? It's an OGC community standard pioneered by Cesium. It makes it possible to stream in massive amounts of 3D content over the web and combine heterogeneous data. Like you can have LiDAR data right next to a CAD model all in the same scene. You can see some debug views here on the right of what individual tiles look like in this 3D model. You can see how this allows the viewer to load higher levels of detail closer to the camera, so you get all the small tiles here, whereas the lower levels of detail are further away from the camera and they can refine as the viewer moves around and explores the scene. And the 3D Tiles ecosystem is rapidly growing. This diagram here is not exhaustive, but it shows you a few of the companies and tools that support 3D Tiles, all at different stages in the 3D geospatial pipeline. So in the top left here we have data providers who collect the data and distribute it as 3D tiles. As you go down, you have tools for generating 3D tiles, and in the top right here, you have clients that use 3D tiles or end-user applications. And as I mentioned before, Cesium Ion has a few global layers that you can combine with your own data when you upload it or use it directly in your projects. The three global ones we have right now are Cesium OSM buildings, which is derived from OpenStreetMap data and has over 350 million buildings. This one is updated monthly and has per building properties like name, address, and a lot of other metadata. We've also got Cesium World Terrain, which is a global elevation layer, down to 1 meter accuracy in most of the US. And like I said, if you use context capture, this is the default terrain layer in the viewer. And finally, we have aerial imagery from Bing Maps, and there's also versions of this with street or city labels or just the roads. Alright, so let's take a look at an example workflow now. Now let's say you're working on a project that involves a proposal for a new bridge, and you have your CAD model and you're ready to share a version of that with stakeholders. Now what you do here is you'd upload this model to Cesium Ion, you'd get 3D tiles, and then you can add that 3D tile set to your iModel project. Now let's take a look at how you do that. So the model we're going to use here is a 3D model of the Golden Gate Bridge I've gotten from TurboSquid. And I've downloaded it here as a OBJ file, but FBX and HLOD and many of the other common formats also work as well. Now here I'm at my Cesium Ion account, and this is the first thing you'll see when you log in. This is your dashboard where you can see all the assets. By default, you have access to the global layers that I mentioned earlier. And what I'm going to do here is I'm just going to drag and drop my OBJ model. This is a zip file containing the OBJ and some of the materials used. And I'm going to select 3D model tile as 3D tiles. Now, if this were a model generated from photogrammetry or LiDAR, I'd select 3D capture. And the only difference there is different types of models are optimized differently in our pipeline. And now once this finishes uploading and tiling, normally if the model had a geolocation embedded in there, it would show up automatically in the right place on Cesium Ion. In this case, it doesn't, so we'll have to geolocate it by hand. Now that this is finished tiling, we can see a preview in the window here. And I can go ahead and edit the tile set location to geolocate this model. I'm going to select Cesium World Terrain as my base layer. And here there's a few different ways to geolocate it. If you already know the exact longitude, latitude, and height for this model, you can enter that here. I'm going to kind of visually do it, so I'm going to enter the address to start with. I know this bridge should be somewhere in San Francisco. Then I'm going to go ahead and find it right here. I'm going to click to position. And here I can see that perhaps the initial scale is wrong, so this should be scaled up a little bit. Maybe just like that. And rotated just a bit. All right, and then once you're happy with this, you can see here I'm using the satellite imagery underneath to make sure I have it in the right location. And then once you're done, you can hit save. And the last thing I want to show you here is the page where you see your access tokens. And given this token, this is what allows another application like iModel to be able to access an asset from your account, and the asset ID, which you can find here. So those two things together is what will allow our iModel project to access this model. Now here in my iModel project, the first thing we're going to do is turn on Cesium World Terrain. Now there's already built-in support for this. You just go to the base layer settings down here, and then you click Use Terrain. And this will load Cesium World Terrain from Cesium Ion. And then to load my bridge model, I've already set up this project to take in a token and an ID, and use that to load the 3D tile set from Cesium Ion. So I'm going to go ahead and paste that in. And there you go. You can see the 3D tile set loading in here. And now that you have this model in your iModel project, you can do all the things you'd normally be able to do here, like save a view, share it with a stakeholder, or take any measurements. And now just to show you an example of a city scale model, I have another scene here with 3D buildings of Philadelphia. And the source data here is actually open data from the Pennsylvania Spatial Data Access Program. And this was tiled as 3D tiles on Cesium Ion. In fact, I actually have the same scene open on Cesium Ion here. And we've come full circle. This is actually one of the important principles about 3D tiles being an open standard, is that you can load the same 3D tile set in all these different engines, so you can use whatever tool works best for your specific project without having to worry about vendor lock-in. And that way you can analyze something in your desktop software, share it on the web, and then someone else, if you give them access, can load it back into a different desktop tool for any follow-up work. And the last thing I wanted to show you while we're here is Cesium OSM buildings. Now I can actually turn it on here in this viewer. And as I mentioned before, this is a global base layer, so it's just a great way to get any context, no matter where you are, where your project is. And if I click on any of these buildings, you can see some of this metadata I was talking about, including the name, in some cases like the building material, as well as the address and other useful metadata. Now I'll hand it off to Ray to tell you a bit more about how this integration works from the iModel side.
Hello. I'm Ray Bentley, and I'm going to be talking about iModel.js and its use of tiles in the display system. Let's start out with a little background here. We're going to be discussing hierarchical level of detail, or HLOD tile trees. These are hierarchical data trees with low resolution tiles at the root and higher resolution tiles in the branches and leaves. And these tile trees are the basis for the iModel.js display system. They have a lot of reasons for that. One of them is superior performance for massive data sets and unlimited hardware. And typically, your infrastructure projects can have huge number of components, massive numbers of facets, and so forth. And HLOD tile trees work well with that type of data and on hardware such as mobile devices or in browsers. It's well suited for streaming, again for browsers, disconnected hardware, and it's useful for any type of geometry, not just BIM data. It's also useful for GIS type data, photogrammetry, and point clouds. And this type of display is a complete departure from what most CAD systems have used in the past. Bentley Systems in particular has not used this technique prior to our development for iModel.js. MicroStation in particular, our desktop, uses completely different techniques. So this is a new area for us in the last 4 or 5 years. Now for a HLOD tile tree to work efficiently, there are two basic requirements. First, the tree must be structured to ensure that the number of tiles for any given view is limited and relatively constant. Two, the payloads for each tile should be compact and organized well so that they can be efficiently delivered to the GPU. If 1 and 2 are satisfied, then performance is independent of the model complexity. Doesn't matter if you have a 100 gig plant design file or a very small design. The performance should be relatively independent of the complexity. One caveat to that is that in iModel.js, we store a single tile tree for each model. So if you have a large number of models, obviously that's going to increase your tile count and reduce your performance. The iModel.js BIM tiles are stored in an octree tile structure, which is loosely based on the OGC 3D tile standard. The tile contents, which we call IMDL, it's loosely based on the B3DM, the batched tile format with a GLTF encapsulated. We've made some optimizations to that to make them performant for BIM type data. And these tiles are produced on demand by the iModel.js backend and cached for performance, which means you may experience a slight lag when you first enter an area of an iModel, but the next time you go back to that area, the tiles will be delivered from the cache and more performant. I'm going to do a quick demonstration here to show how the BIM tiles work in iModel.js. Now I've turned on a diagnostic tool to show the boundaries of the tiles so that we can see what's actually happening as you work in iModel.js. Here in a zoomed out view, you'll see there's only a handful of tiles, but as I zoom in, you can see the number of tiles increase, and if you get in fast enough, you can see that you actually see the coarser tiles being replaced by the refined tiles. Again, I'll zoom out. When I zoom out, it goes back to the large, low resolution tiles. Now, as a matter of demonstration here, I'm going to use a key-in to freeze the tiles. And then let's go back in, zoom in, and see what those tiles. Now remember, this is a frozen view of the low resolution tiles for the fitted view. And as I zoom in here, you could see those tiles, these curved surfaces are actually coarsely faceted. You could not see that because it was smaller than the screen resolution when you're zoomed out. But as I'm in a frozen view, a frozen scene, you could see what those tiles actually look like. If I then go back and unfreeze the scene, you could see it refines and goes back to the large number of tiles. Here's a couple of quick images to show what's actually happening with the tiles in a camera view. To the left, you could see the view that we're looking at. To the right, you could see the viewing frustum and the tiles that are actually displayed. And as you could see, near the eye point, there are many high-resolution tiles. And as you get further off into the distance, the number of tiles decreases with lower resolution tiles. Okay, now I'm going to switch gears and talk about the 3D tiles standard. The 3D tiles were introduced in 2011 by the Cesium team at AGI as an open source project to support scientific visualization on the web. The 3D tile standard is supported directly by iModels.js and is used as a source for photogrammetry and point cloud reality models. It's an open and interoperable standard, and there's the GitHub repo. 3D tiles was accepted as an Open Geospatial Consortium standard, and it is the format that we use to store context captures web-ready 3D scalable meshes. It's a heterogeneous format. It includes B3DM, which is essentially GLTF with feature tables. The PNTS format, tile format, is for point clouds. I3DM supports instance data, and CMPT supports composites of the different formats. Here you can see 3D tiles in action. This is a reality model captured by context capture, and you can see the substation model integrated with the actual BIM components. iModels.js uses 3D tiles for display of point clouds. It uses either the 3D tile format with PNTS tile payloads or a proprietary format that was developed at OrbitGT, a recent acquisition, which is highly optimized for point clouds and streaming in particular. And on the screen, I have a point cloud. As I'm zoomed out, you could see the basic octree structure. And as I zoom in, you could see the tiles refining. Now, one thing that we do with point cloud is we display larger points when a coarser point cloud is displayed, and that kind of softens the transition between a lower density tile and a higher density tile. Now, 3D tiles can contain batch IDs and feature tables to allow features within the tiles, but in general, reality models do not contain these features and are essentially monolithic. Spatial classification allows the reality model to be treated as sets of spatially delineated objects. And the classifiers are separate spatial models that can be either volumes or extrusions of 2D planar footprints. And by separating the classification from the reality model, the classification can persist as the reality model evolves. Now, in volumetric classification, the classifiers can consist of any closed watertight entity. And this is suitable for true 3D BIM models as opposed to 2.5D GIS models. It's also useful for automatic classification when reality model photogrammetry is recognized by machine learning, which can then automatically generate the classifier volumes and their associated properties. Okay, let's take a quicker look at volumetric spatial classification of a reality model. I have a reality model of a substation created with context capture. I have some volumetric classifiers. You could see they're just simple bounding boxes with properties. But when I move over the objects in the reality model, they behave as classified. And if I click on those, I'll see the classified properties. Switchgear, transformers, coolers, and so forth. Okay, let's take a quick look at planar classification for 3D reality models. We'll look at the classifiers first. Essentially what I have here is a bunch of GIS data for the Philadelphia area. I believe it was originally derived from Esri data. And we have large colored polygons for the commercial corridors, smaller polygons that represent the buildings. The dots are streetlights, and the linear data is the arterial streets. So let's go ahead and see how those can classify a reality model. We'll turn on our reality model. The first thing you see is the building footprint classification. And essentially, I can click on any building and see the properties for that building, the height, and so forth. If I then move to the streets, I can go in and look at any street, highlight the street, and see its information. If I go to the commercial corridors, and as you recall, these were colored, and the classification for the streets will include the I've set it to colorize the reality model by the classifier color. And there you could see information on each of the commercial corridors in Philadelphia. Finally, we can look at the street poles. And I've got information on every street pole in Philadelphia with a little dot that denotes the location. That's it. Cesium World Terrain is another case where iModel.js uses hierarchical level of detail tiles. It's basically a source that Cesium aggregates from worldwide terrain sources and provides a default terrain that iModel.js users can use worldwide. You see the resolutions listed there, and this is their terrain for the Grand Canyon. And as you can see, it's fairly high resolution. Okay, the final type of tile that I'm going to discuss is map tiles. And map tiles are essentially a hierarchical level of detail tree with 2D tiles. And in iModel.js, we project those tiles into the geographic coordinate system of the project within the project extents, so that the map data always aligns with the project coordinate system, no matter which system the map tiles originate in. And then outside of the project extents, we project them to the Earth ellipsoid, and you can see that in the image on the right. The map server formats we currently support are WMS, WMTS, the tile version. We support the ArcGIS REST API directly. We support Azure Maps, Big Maps, and Mapbox. Now, some of these servers are supported as tile servers directly, in which case we get cached tiles from the server. And other ones support essentially image servers. And on an image server, we kind of work with those as a pseudo tile server, where we'll suggest an image for each tile. In general, the tile-based servers are faster, and the image-based servers are less performant. And I'll give you a short demonstration on that in the next slide. Okay, I'm going to give a quick demonstration of map layer support. This is the area around Bentley Systems headquarters, and I have a couple layers here. One of them is a WMS server that is showing hydrological features, and the other is a Chester County server. It's an ArcGIS REST server, and it's showing some data from Chester County GIS sources. And I can go into these sources, and the Chester County source has different areas, and I can go on and turn on different things. This is turning on information about the soil data. I can go and reorder the layers. Now the hydrological layer is on top. I can come into the layers and control their transparency. Now let's move to the Grand Canyon again, and I just wanted to show here quickly that the map layers work with terrain as well as flat map data, and this is showing the hydrological overlay for the Grand Canyon. In summary, the use of the hierarchical level of detail tile tree is fundamental to iModel.js and the display of large digital twins and their associated data. In the table below, I list the different tile trees that are currently in use, their formats, and also I included the location of their source files and the main source files that implement them in case you're interested in diving into the details and the guts. Thank you. We'll pause for some questions now.